Salam and welcome everyone. So today we're going to be working on the question on the screen that says when standard enthalpy of formation of ethylbenzene is negative 12.5 kilojoule per mole, calculate the standard enthalpy of combustion. So the first thing you have to do is the standard enthalpy of formation of ethylbenzene is this. We're told the standard enthalpy of ethylbenzene. So we're just going to say ethylbenzene is EB for now. So that would be standard enthalpy of formation. So like this, okay, of ethylbenzene, so EB, is going to be equal to negative 12.5 kilojoule per mole. Now we're asked to calculate the standard enthalpy of combustion. Now, one thing you have to note is that in a combustion reaction, this is a reaction that occurs whenever a molecule is reacted with oxygen. So this was taught to you in your Gen Chem classes, and now you know that information that you're going to apply to this PChem course. So ethylbenzene is actually of the structure, even though the structure is not exactly what we need in this question, it's just going to be something that will help you anytime you're not given the actual structure or molecular formula, right? If you're not given the molecular formula, you can draw out the structure to determine whatever this is. So this is ethylbenzene. You have the benzene group right here, and then you have the ethyl group. Sorry, you have the ethyl group right here. So that's how it is. So yeah, you have the ethyl group right here, and then you have the benzene group right here. So this is basically ethylbenzene. So some of you may be wondering, why am I like being too like why am I like talking about every single thing like very intensely? It's because I want everyone to be able to be on the same page, because you need to be able to get every single part of this information in order for you to do well. So yeah, so we're gonna count now how many carbons and how many hydrogens we have, so that we'd be able to do the reaction. So you have one carbon, two carbon, three, four, five, six, seven, eight. So you end up with C8. Then we'll have to determine how many hydrogens. We know we've got two here. So this is CH2, we have CH3. So this place has five hydrogens. This place has no hydrogen because there are four bonds. So that would be one hydrogen here, another hydrogen here, third, fourth, and fifth. So five hydrogens plus the five hydrogens in ethyl group is going to give you 10 hydrogens. So you have C8H10. So rewriting this, we have C8H10 plus the combustion reaction, because we're asked to find the standard enthalpy of combustion for the reaction. So this one here, or the standard enthalpy of combustion, basically, yeah, for this particular reaction. So we're supposed to naturally, anytime you have a combustion reaction, you're supposed to always have carbon dioxide, CO2 gas, as well as H2O and water, which is in liquid form. So this ethylbenzene is a liquid, and of course oxygen gas is a gas. So now we're going to balance this chemical equation, because that's the next thing you have to do. So you can see that we're each inching into the question, right? Calculate the standard enthalpy of combustion. So now we're going to balance this equation. So you have eight carbons here. We have one carbon here. In order for us to balance it right, we're going to put an eight here. So now we have the carbons are balanced. We have oxygen here. 2 times 8 is 16. So we have the balanced carbon here, but we have then 16 oxygens here. And then we have how many hydrogens here? We have two hydrogens here. We have 10 hydrogens here. Well, 10 hydrogens and 2 here. In order for us to balance it, we know that 10 divided by 2 is 5. So we're going to put 5 here. So now we've balanced the hydrogen. So now we have the 10 here. And of course, we have the 10 here. So now the only thing that remains for us to properly balance, in order for us to have a balanced chemical equation, is actually oxygen, because we're done with carbon, we're done with hydrogen. And both left and right side of the equation have the exact number of atoms. So next we have to determine the number of oxygens we have on both sides. We can see that on this side we only have two oxygens. On the left side we have two oxygens, right? And then on the right side we have eight, 8 times 2 is 16. So we have 16 oxygens, and then we have for CO2, and then we have um 5 oxygens in the H2O. So that's 5. So making a total of 21. And then we have 2. How do we go from 2 to 21? Well, 21 divided by 2 is the same thing as 10.5. So we have 10.5 here, or we can just say 21 divided by 2. So when you look at all of this information, you would see that everything is balanced, right? We have a total of 8 carbons on both sides. we have a total of 10 hydrogens on both sides, and we have a total of 21 oxygens on both sides. So 21 divided by 2, this 2 you can think about it like you're canceling out, or you can just say 10.5 times 2, which is 21. So that will be 21 oxygens on both sides, right? And then this one, you have 16 plus 5. So that's a total of 21 oxygens on both sides, right? So that's it. So now we're just going to rewrite this equation. So that's basically our work. Since the combustion reaction is a reaction, you can just have, or since combustion is a reaction, you can have the change in enthalpy of combustion to equal this formula here. And I'm going to explain the formula to you. So you have this, and then you have the change in enthalpy of formation, okay, or change in standard enthalpy of formation minus this here as well. We're just going to write the same thing. But then you may be wondering, well, why are we writing the exact same thing? Well, this one is for products, okay, and this one is for the reactants. And this V here is just the stoichiometric value, meaning the coefficient or the stoichiometric coefficient. So this V here is going to be whatever is in front of the molecule. So if you have 2O2, this V here is going to be the stoichiometric coefficient of oxygen gas of O2, which in this case is 2. I'm just basically showing you what's going on here. So now we're just going to rewrite everything that we have. I'm going to break it down. We know now that we're gonna sum up the standard enthalpy of formation of the product, and we subtract it from the standard enthalpy of the reactant. So this is what this is going to look like now. So we have this here equals 8 standard enthalpy of formation times CO2 gas plus 5 times standard enthalpy of formation of O2 gas, or H2O gas, sorry, H2O liquid. Why am I saying H2O gas? H2O liquid. So I'm just showing you what we're doing here. So you can see now that this first part of the information involved just the product. So the right side of the equation, the CO2, we have the coefficient at the front, and then the standard enthalpy of formation of just the CO2, while we brought the coefficient of CO2 to the front, and then plus we brought out the coefficient of H2O to the front, multiplied by standard enthalpy of formation. So basically, this is how you put down the structure of the information. Then you say minus, we're going to do the one for the reactants. So that would be enthalpy of formation of C8H10, okay, liquid, plus 21 over 2 is going to be brought forward. And then, of course, standard enthalpy of formation of O2 gas. So this is basically how it's done. This is how you structure or write out the structure of this part. Is very, if not the most important part of the question. So let's not forget that we've been given the standard enthalpy of formation for ethylbenzene. So this is the whole point. This is the reason why we have this. So let me rewrite the standard enthalpy of formation of ethylbenzene. So that would be that we had for EB here is the same thing as the standard enthalpy. If you look at your question again of C8H10, okay, liquid. So all of that information is negative 12.5 kilojoule per mole. I'm just rewriting it so that on this part of the question, you'll be able to know what you're doing. So yeah, so now let's go on to input the information and to substitute. We know now that 8 times the standard enthalpy of formation of CO2 gas. Some of you may be wondering, well, they only gave us the one for ethylbenzene. They did not give us the one for oxygen. They did not give us the one for H2O. They did not give us the one for CO2. Many times when you have questions like this, there's going to be a resource section of your textbook that has all of this information. So right now, they didn't give us the standard enthalpy for CO2. So if you're doing an assignment, you have to go to the resource section of your book and determine what the standard enthalpy of formation for CO2 is, and for H2O and for O2. They would not give it to you if it's an assignment. Maybe in a test or an exam, they're going to give you all the values for you to do it. Or maybe there's going to be a resource section for the quiz or for the exam. But just note that you can find this information on Google, or you can find it in the resource section of your textbook. Looking at textbook, I see that standard enthalpy of formation for CO2 is negative 393 0.51 kilojoule per mole. So I'm substituting. This is where I am right now. Okay, that is the standard enthalpy of formation for CO2 gas plus 5 times the standard enthalpy of H2O gas. I'm right here now. So make sure you follow this, the resource section of your book. I'm purposely not writing it out separately for you guys because I want you guys to be actively searching for it as well. Because in an exam or in on assignment, you're not going to have me here writing out the information for you. So you have H2O, the standard enthalpy of formation. Looking at the research section of my textbook, I see that to be negative 285.83 kilojoule per mole. Okay, so that's that. And then that is the information here, minus the standard enthalpy for ethylbenzene. We're given this one, luckily, is just negative 12.5 kilojoule per mole, and then plus 21 over 2 times the standard enthalpy of formation for O2 gas. Looking at our information, we see that that is just simply zero, meaning everything right here is just zero. So of course, you input your information in your calculator. You have 8 times negative 393.51. We have that to be negative 3148.08 kilojoule per mole. Okay, minus negative 1429.105 kilojoule per mole plus 12.5 kilojoule per mole. So yeah, all of this information right here would be standard enthalpy of combustion is going to equal negative 3148.08 minus negative 1429.15 kilojoule per mole will actually give you and all of that information plus 12.5 kilojoule per mole. So when you put all of this information in calculator, you end up getting negative 4564.73 kilojoule per mole. And as you can see, this information is in one decimal place. So you can just put this here and you can say the enthalpy of combustion that you're asked to solve is, and so yeah, standard enthalpy of combustion is negative 4564.7 kilojoule per mole in one decimal place. That is the answer to this question. Or you may be asked to solve this based on the fact that this is 12.5 kilojoule per mole in the question given to you, and that's 3 sig figs. You can also say the answer could be, depending on what you're asked to do, it could be in 3 sig figs, it could be in decimal places, whatever you're asked to do. So that would be negative, in 3 sig figs, that would be negative 4.56 times 10 raised to the power of 3 K kilojoule per mole. And this is just basically the answer. I wish you guys all the very best. If you have any questions, please leave it in the comment section. And I wish you guys all the very best. Assalamu alaikum warahmatullahi wabarakatuh.